Good morning, everyone. Thank you for joining us today. Thanks for jumping on nice and early. We will be getting started in about 4 minutes time. But for now, you've got some time to go and grab a quick coffee or heat your lunch up. We will be kicking off shortly. At the bottom of your screen, there's a Q&A section. You can pop your questions in there at any time, and we'll answer as many of those as we can at the end of the session. And the webinar has been recorded, and we'll share that with NZGS members in upcoming newsletter in the next couple of weeks. But for now, we'll just give it 3 or 4 minutes and then we will kick off. Thank you. Good morning, everyone. Thank you for joining us. Just doing another sound check for those that have joined in the last couple of minutes. We will be starting just after 12. We've got great registration numbers today, so we're going to give everybody the opportunity to get on. But thank you for joining nice and early. There's a Q&A section at the bottom of your screen. Please feel free to pop your questions in there at any time, and we'll answer as many of those as we can at the end of the session. And the session has been recorded as well, and we'll share that with NZGS members in the upcoming newsletter. We'll also look to put it on the NZGS website. As I mentioned, we'll kick off in perhaps a couple of minutes time, but for now, we will be patient. Thank you. Afternoon, everyone. I can see the numbers slowly ticking up there. Thank you for joining us today. We will be getting started very, very shortly. At the bottom of your screen, there's a Q&A section. You can pop your questions in there at any time, and we'll answer as many of those as we can at the end. And the webinar is being recorded, and we'll share that with NZGS members in an upcoming newsletter, as well as on the NZGS website. I can see the numbers ticking up very nicely. So I think with that, being conscious of time, I would like to hand over to Christoph, who will be your facilitator for the session. Over to you, Christoph. Sorry, Christoph, your sound doesn't seem to be coming through for some reason. Are you having that same problem, Matt, or is it just me?
No, I can hear you loud and clear, Holly.
Can't hear me.
Is that coming through?
There we go. Yes, there we go. Coming through now. You clicked the button.
Was muted.
That's all right. We'll start that again. Thank you.
Cool. So sorry about that. Yeah, I'm one of the NZGS Wellington branch coordinators, and definitely our pleasure today to welcome Matt to give this presentation. Matt is a geologist and spatial data scientist at GNS Science, and he specialises in structural geology, 3D modelling, analysis of digital data related to geological mapping, aggregate and critical mineral potential modelling, and the application of remote sensing and drone imagery to geoscience research. He's part of the Geological mapping and stratigraphy team who developed new maps and is particularly involved in the new urban mapping projects across Auckland, as well as ground-shaking studies in Wellington. Matt completed geology and business undergraduate degrees, as well as his master's degree in geology at Victoria University of Wellington, and he's currently in the final stages of his PhD in structural geology from the University of Western Australia. He started work in the industry as a geologist and spatial analyst for Kinex Limited in 2005 before joining the team at GNS in 2015. And I think that gives a really nice intro to Matt to show the vast variety of experience that he has with modelling geology. So with that, over to you, Matt, to talk about Wellington geology and 3D modelling.
Great, thanks, Christoph. Can you hear me all right there? All good? Okay.
Yeah.
Right. Right. So thank you very much for having today. I'm going to talk about the modelling we've been doing in Wellington, but with a bit more of a focus on the data that goes into the models and what you can do with them afterwards, rather than a tutorial on how to build a 3D model. So these models, we've been building them to help us understand the natural hazards in the area and also to assist with engineering geology. So I'm going to start off with what's the purpose of a 3D model? Why are we going to, why do we want to build 3D models? Then have a bit of a chat about the history of modelling in 3D in Wellington. For those who aren't from New Zealand or the Wellington region, just give you a brief overview of the Wellington geology, and then run through some of the data that goes into the models, some of the surface mapping, borehole records, geophysics, the expert knowledge, and then a bit about creating the 3D models that we use, and then how those model results are applied to other research. And then I'd like to touch on uncertainty and confidence in modelling data. So Christoph did a great job of introducing me. Thank you very much. So in case you're just joining us, I've been with GNS Science now for 6 years, and I've been creating digital models for about 15 years. And it is a passion of mine, trying to express what's below the surface from our observations at the surface or from boreholes. So why create 3D geological models? Well, if we just work in sections, it's a bit like looking through a mailbox slot. You just see that one view, you can't. But when you work in 3D and you pull in all your data from all around, it's like looking down the hallway with the door wide open. It's just a whole new way of visualizing and interpreting and interpolating your data. So working in 3D is a whole other step up. So I think this top quote here, it's one of my favorites about why we create what a 3D model is. It's an approximation of reality created for the purpose of problem solving. So as a 3D modeler, I'm well aware that I'm just creating a model that's a set of data for other people to do great things with. But there's a lot that goes into creating that model, but I also need to be aware of what the end use is or what the model's intending to solve. So before we start any modeling process, I consult with potential end users. And this is quite easy if it's just a single use case for an engineer or a single geological study, because you can build your model and your units to solve that one problem. But it is more of a challenge for us at GNS Science. For those of you overseas, GNS Science is the equivalent of the New Zealand Geological Survey. So we have a lot of end users, and we need to try and make the model useful for solving multiple problems. So that's a real challenge. So it takes a bit of planning at the start and communication with our stakeholders and some imagination too as to what it might be used for down the line. And there's three really big challenges at the moment in the 3D modeling industry, both in New Zealand and overseas. And one of those is the limited availability of subsurface data. Those all critical boreholes or deep geophysical surveys that tell us what's under the subsurface. And then good centralized storage and accessibility and searchability of all that data. It is getting better and better these days with big databases coming online, but often combining databases or finding that data is just a scan report, not in a digital form, can be challenging. So it's the accessibility of data and those data lakes and data warehouses that's It's coming online, but it's still a challenge. And then a big challenge is also sourcing scientists that can both manage the data, understand the data, and model huge amounts of it as it becomes available. So training our new young geologists and geotechnical engineers, if they're interested in this sort of work, and a whole suite of skills that allows them to become a digital scientist. So a bit about the history of 3D modeling in Wellington. It started really back in, the first digital geological model started back in 2010 with work by Stephen Simmons here in the Wellington CBD, and by Boone and others in 2010 up here in Lower Hutt. And then we really started to model the Wellington area in 3D again after the Kaikoura earthquakes. And so that started another model of the CBD, a revised one in 2018 that I was part of. And this new modeling, I'll talk about a bit in a minute, but it was a whole other generation of 3D modeling software, data availability, boreholes, collaboration between universities. It was a real new, start of a new era of 3D geology. At the same time, John Begg has been working really hard on remodeling the Lower Hutt area here through into the harbour, and this was for a groundwater project. I think that's still ongoing. And then we've been working, we've done some models in Upper Hutt, another critical basin area in New Zealand, and Porirua, and then the entire Wellington city area here. We extended the border out in 2020 for the City Council. And the two current projects are this blue outline here, this red outline here of the Wellington city area. So it's it's a subset of our larger model, but it's where a lot of our data is concentrated, and the populated areas of Wellington too. And the populated areas are important from a hazard point of view for the end use of the model. And the entire Wellington region, a large scale, that this whole black box and area of the model here, a large scale model for being used in numerical modeling for ground motion and hazard studies. So we're sort of covering the whole region at all sorts of different scales and different data sets. So as I mentioned, there was quite a step up in the type of, in the way that geological modeling was done between 2010 by Simmons and the modeling that I was involved with by the report by Kaiser and others in 2019. Obviously, the modeling software changed, as I mentioned. The availability of data changed a lot, and accessibility changed as well. But also there were some big changes in just what we knew about the geology. For example, these two models are about the same view with the Wellington fault down one side. But you notice that the new model's got a new fault down here, the Aotea fault, which was interpreted by NIWA in, I think it was 2017 or 18. So instead of having a basin that onlapped on one side and was fault controlled on another, the basin suddenly became fault bound, and our interpretation of that, of the stratigraphy and the way the model was built, changed as well. So I'm just going to show you just a few shots in the model so you can see the different styles. This was the one done in 2020 for the whole Wellington city area. Again, focusing on the basins where there was sediment for understanding the ground shaking. The large regional model used in ground motion simulations recently. And then some of our work in Upper Hutt, out in Porirua, and the work by Boone and others in 2010 in Lower Hutt. So you can see different styles of modeling, modeling different properties and units, and different software packages. So Wellington City is it's an active tectonic setting. We have the active faults. We have the one that most of you know about is the Wellington fault that runs through here through the hills along the eastern side of the harbour, and then up through the Hutt Valley. The new Aotea fault, which isn't on this map, but it runs up through here. And then we have areas of these sedimentary deposits. So you've got Wellington City and Upper Hutt, Miramar and Rongotai, and other pockets of sediment all around Wellington. And the sediment, it sits on top of a grey-wacky sandstone basement. So you can see here, there's a oblique view. Here's the Lower Hutt area, heavily populated, Miramar, Rongotai, and the Wellington city area and the CBD as well. A very important infrastructure and populated area for Wellington. So and if you were to take a schematic cross-section through Wellington, it would might look something like this if you were lucky enough to get every single unit. So I apologize for how crude this cartoon is for the stratigraphers out there. But basically, we have a setting where we've got a whole lot of basement geological units under here, but mostly Rakai terrain greywacke sandstone. And then we have generations of sediment that have been infilled on top of that and deposited on top of that basement and then eroded away, and then more material coming in through the glacial and interglacial periods. And then right on top, we have our anthropogenic fill in the last 100 years that's been put on top of it all. So we cover a couple of 100,000 years of sediment sitting on top of a very old Cretaceous and Triassic basement. And locally, if we look at some simplified boreholes throughout the region, you know, they all intersect basement at some point, but we have different thicknesses of the mid-Pleistocene and the late Pleistocene units going through, and different thicknesses as well of the Holocene group. So the different regions of Wellington and basins have their own histories. So it's quite a challenge to model over a whole region and finding the common geology between the basins. But in general, what we're looking to model are the Holocene sediments, because these are the softer, near surface material, our late Pleistocene material, if we can map out the interglacial marine layer, and then our older sediments, which are usually denser and behave differently during an earthquake and on top of the basement terrain as well. So that's what we're trying to model through to express the geology of the area. Now, the process of geological modeling, you might just think that you just download the latest copy of Leapfrog or GeoModeler and away you go. But really, you're only coming in at this step here. So there is actually a huge amount of work that goes into just getting to the point of opening up your 3D software. You've got all the work of data mining, cleaning, and storage, storing all your geological and borehole data and geophysics. And you know, these days you need a data engineer or a scientist to be able to cope with all of that. Then you've got all your spatial analyses to do to take this data and turn it into something that's useful for geoscience. And then usually you need to take that again, and you need your geologist or geophysicist to start doing things with it to turn it into a geoscience product. Then, if you're lucky, you might be able to start 3D modeling with it. But it's usually iterative. You'll go back and you'll add more, you'll consult and you'll tweak, and you'll come back and forth until you get yourself a 3D model. And then there's all the end use of the model. Like I said at the start, if you're a 3D modeler, you start to get used to the fact that the product you present at the end is not just for pretty fly-throughs and pictures, it needs to have an end use. And that's where all these clever people, the numerical modelers, the geotech engineers, the groundwater folk, they all then take this data and then hopefully do great things with it, and then give me feedback too, or give the geological modeler the feedback so they can go and tweak it for future use. Now, sometimes this entire process will be done by one person, and that's quite feasible if it's a small project area and there's not that much data and spatial analyses to do. Other times you're working with a whole lot of individuals and the data is passed along, and you're working as a large team and each person is quite specialized in each area. Now, exactly which process you want to do, it varies from company to company and from industry to industry. Personally, I tend to focus on these front four here. I do a lot of the data and spatial analyst work right up to 3D modeling, but when I get to this point, I pass it on to very clever people. But one of the great things about working for Geoscience is that I can have help from experts all the way along. I can go knock on doors and ask for help as I go, or bring other people in to help. But exactly how you do it in your company depends on the project and obviously the type of background you have as a geoscientist. So creating these models, first you need to start off, you need to define your purpose. As I mentioned at the beginning, why are we creating these? Are we creating them for ground shaking? Are we creating them for stratigraphy? Is it strictly hazard and urban planning? What scale are we doing them at? So we need to really define our purpose or purposes before we even get started, because that defines the type of information we're going to be using and the outputs and the units that we want to model. Then begins the data compilation phase. And for a big model, this can take up to a year. in some cases, if your data is not that clean, pulling in all your geological mapping, if maybe doing new mapping, collecting new geophysics in areas where you've got data gaps, and getting all those borehole records in line. Then the modeling begins. And one of the key steps is determining which units you're going to model. What are the layers going to be? How are you expressing your geology? Often your geological map will have scores of different geological units, but not all of those are suitable to model in 3D. So you need to lump or split or reinterpret the geology with this end purpose in mind. This is quite important. Then there's all the spatial analysis that you can do that you do in your GIS or in your databases, and then you start building your 3D surfaces and building the geological model. So you can see that step's right at the end. And so the actual building of the 3D model is probably only about a quarter of the entire process as far as time goes. Then there's the creating of the derivative products from the 3D model. And this is often usually done by the 3D modeler themselves. They'll output all these different units, and then they go off for, like those other clever people I was talking about before, to start working through and creating some of these outputs. So, we've got our geophysics, our geological maps, our borehole records, all go into creating that 3D model that then has these derivative products like site period, for example, here that we can forward model out. So I'm going to talk a bit about borehole data. Borehole data are one of the most critical subsurface observations of the geology that we can get. I mean, I can't go underground and look at the rocks, not yet, and I'd hate to fill in that health and safety form to do that. But most of the time, boreholes they've been historically drilled for petroleum, geothermal, mineral stratigraphy, groundwater, geotech investigations. But where a lot of our 3D models today that we're focusing on here at GNS Science are for the urban areas. So we wanted to use them to help with geotechnical evaluation, understanding hazards. There's a lot of work going on, of course, in the geothermal and groundwater areas at GNS, but my focus is in the urban areas where the drilling data is somewhat limited, and if it is there, sometimes it's very shallow, so it doesn't really tell us about the whole stratigraphy. Or maybe if it's not in a database that we can get to, they might have never been drilling there, or the results are confidential, whereas as just said, they're not in a searchable database, so we have to somehow hunt them out. So one of the real game changers in New Zealand for the borehole data has been the New Zealand Geotechnical Database. So the New Zealand Geotechnical Database was developed for geotech professionals and engineers to share borehole information and to permanently archive the records away, so they're accessible for people in other companies or on other projects, and in return having access to all the data as well. So it's been absolutely fantastic. This is a screenshot here of the NZGD website showing all the boreholes and down onto the waterfront in Wellington. And you can click on any of those and pull up the PDF reports, which is absolutely brilliant having that information at your fingertips. Unfortunately, they are PDF reports, most of them. Sometimes you'll get an AGS digital file, which is great, but it's more of a library than a database at the moment. So that we need to go through and data mine the records out into a digital database. So we've utilized that data from the NCGD and from GNS records and other records all around Wellington and some other places in New Zealand to compile our borehole database. So some previous compilations, first by Simmons in 2010, he did quite a sizable compilation of what was available prior to the NZGD being available for the 3D model in Wellington back then. And then we built on that in 2019, recently for the Wellington City Council project in 2021. And now with the current project that's running under the National Seismic Hazard Model, we've got nearly 5,000 boreholes in our database for Wellington, and they comprise of open and closed file or confidential borehole data that we use for our research. So you can see just the amount of data creeping up over time as we've had both funding to combine it into a borehole database, but as also as new types of data coming through, like this downhole shear wave velocity data starting to come in after 2010. And yeah, so we're really seeing an increase in our knowledge of the subsurface through this borehole data. So then you need to build a database. And if you like databases like me, then this is great. You get to link all your tables together and you can visualize it in Access, and it's sitting back and with lots of clever people that keep it tidy in the background, and you append all your data in. But there's a lot of typing of information and copying and pasting in and making sure it all works. And when we mine our borehole data, we type in all of the details of the descriptions that your geotech and stratigraphers write in your borehole logs, not just the interpretation part, but we'll take all the raw data right down. And this is really handy for down the line, reinterpreting your hole in 3D or in 2D. If something doesn't look quite right, you can instantly pull up that original description of what was there. So we're not taking any shortcuts with the data mining, and it has paid off having all that data accessible. One of the things we have done along the way is, because we know not all borehole records or wells are the same as far as quality goes, is we've given them each one a subjective ranking. And when you've mined out a few thousand over your time, you start to develop a sixth sense for good boreholes. Like these great ones by engineering companies these days it's well described, lots of information. You've got information about water, you've got other geotechnical properties like SPT, all in a nice digital log. And then you've got some older ones, they can still have really good descriptions, even though they're old and handwritten. The stratigraphy and rock descriptions are still really good. But some of them you just don't, just outputs from an old database. For all we know, they could have been written on a napkin at the pub by the driller at the end of the day. We just don't know. So we give them a subjective ranking based on quality, so that when we are looking at all the borehole data, if there is something not quite right and a borehole's throwing the 3D model off, we can remove it and we can justify it by the quality of the borehole log without having to pull up the original record. Or if we just wanted to use just our high quality data, we can instantly filter our 3D model by our borehole quality. So that's and it's subjective, but as I said, when you've done a few thousand, you start to get a pretty good understanding for where the quality of the borehole sits. So one thing we did in Wellington is we took all the boreholes and we reinterpreted the lithology and engineering properties for them. So the reason we did this was because the interpretations that a person makes when on their borehole log at their site is often just relative to their site. And we wanted to reinterpret the units for something like the set of stratigraphic definitions here that would link the data all across the Wellington region. So we're both taking a stratigraphic time into account, but also dense and loose properties from an engineering point of view, and different types of basement. So trying to set ourselves up for the future when we interpret these. And then not just interpreting the log from a bit of paper on my desk, but looking at it based on its 2D and 3D position to other holes. So maybe one hole only gets down to 8 meters, it hits a dense layer and they stop and they pull out. But all the other logs, maybe 3 other holes around it went down to 30 meters and they went through that same dense layer, but then went into another loose layer and then didn't hit the loose dense contact until much deeper. That first hole, because they didn't penetrate through that dense layer, that if we just interpreted that one by itself, we wouldn't have known that that wasn't the true horizon. So taking into account the 2D and 3D position when interpreting the logs has been really useful. And particularly useful for interpreting the top 30 meters of the sediment, which is really critical for that loose dense contact and ground motion and ground shaking studies. Right, so one of the next steps in our modeling is defining what units or lithology we're going to have in our 3D model. And for Wellington, we want to understand the anthropogenic fill, because that has quite different seismic and ground motion properties to the naturally deposited sediments. We have our marine sediments, which are a bit softer. And then we have our quaternary alluvium, which in Wellington is often just a mix of colluvium, alluvium, maybe it's marginal marine, got some sand and silt and peat coming into it, but without particularly good geochronology through this quaternary section, we decided just to lump it together, but split it into loose dense and very dense for engineering purposes. And I'll go into a bit more about that loose and dense classification in a minute. But so we've got a first pass at our units that we're going to have in our geological model based on the end users that are going to use it. So for our loose dense evaluation, we pull up our good old NZ GS soil field guide sheet, and in there it tells we're going to use their classifications of what a loose, dense, and very dense soil or material is. And basically we're using that SPT, those penetrometer values, those N values. If they're less than 30, then it's loose. And then we're looking for that contact then into dense where it consistently goes over 30. So you may hit a gravel layer I was talking about before at 7 or 8 meters, but then you go back into soft silts and things like that. So in that case, that gravel might be up in the middle here, but we keep on going until we consistently see that we're into dense material. And then very dense, often you don't get SPT measurements down this far. If we're lucky, we can get downhole shear wave velocity. We're sort of talking something over 600 meters per second in shear wave velocity, or when the geologist or geotech starts to describe the material as becoming very dense or very stiff, or using those words that describe that show this change. And it's usually about between 50 and 70 meters in Wellington, that change. But one thing we noticed when we were going through all the borehole records, reevaluating all the stratigraphy, was that the younger, the typo there, that should be the younger late Pleistocene sediments, their loose dense contact was a lot deeper down than the older mid-Pleistocene ones here. So which makes sense. The older rocks, they've been buried for longer, they've possibly been compacted, so it makes sense that they're a wee bit denser and have different material properties to the younger ones. So we thought maybe in our 3D model, if I go back a slide, just having these three, maybe it changed as we move across into different lithological regions in Wellington. So we started to split them off into, based on the different regions, we started to split them into the different geology. We started to split the loose, the dense, and the very dense. And this was also starting to make sense when we looked at our downhole shear wave velocity. We were seeing a different fit profile. So our the shear wave velocity through our older rocks here, the mid-Pleistocene, is a wee bit quicker than our late Pleistocene. You can see here the spread's a lot greater in our late Pleistocene, which when you've seen the logs and you see all the different material types, that makes sense. And here's that blue line from the chart above, showing it sitting down below here. So using some of this downhole geophysics is really helpful as well. So what we've ended up doing is extending all of our units in our 3D model to quite a few now, but you can see here we've split our loose sediments into late Pleistocene and mid-Pleistocene. So we've got loose for each and dense for each. And then we've also added a transition unit here between the loose and the dense based on our analysis of the downhole shear wave velocity and also some other surface wave modeling that some of my research partners have done. One question that's still baffling us is what we do with the basement. Is there a weathering profile down here that we should include as far as the modeling for this sort of thing goes? Yes, we should include it, but at this stage, we're not quite sure what's happening there. So that's one for the future. So geophysical data, there's been lots of geophysics done in Wellington, lots of HVSR work by GNS Science and Auckland University and Canterbury University, lots of multi-channel surface wave analysis too. So these are all really good for interpreting where in areas where we don't have borehole data collected. And also gravity is urban gravity data collection is taking off now. There's great work done by Alistair and Tim recently that was published here in New Zealand. Huge amount of gravity data collected and model giving us a new depth basement map, which is really helpful, and certainly getting into some of those interesting urban areas that are critical for understanding our basement a lot more. But out in the harbour and other areas of Wellington, you know, there's been a lot of geophysics done historically, a lot of seismic and gravity, and some more urban geophysics done here recently by GNS to understand some the geometry of the basin out in Rongotai. And then out in the harbour for many years, NIWA have been collecting shallow seismic. So we worked with them recently, and they produced nearly 250,000 interpreted depth points for the some of the top horizons in Wellington Harbour to use in our 3D models, and that's just a massive amount of data. That's but it's helping us understand a really critical horizon in our 3D model offshore. So what the next set of data that we really need for our 3D models is our geological map. It's our first section. It's our top base. It's where we often know the most about the rocks. So we've updated this using a lot of historic geological mapping and data, as well as our surface. We're putting in our borehole data as well, looking at the surface records. And LiDAR has been brilliant at helping us define those boundaries between our geology when at an urban mapping scale. If we're sort of pulling in data from 1 to 50 or 1 to 250,000, using the LiDAR to refine that boundary for our urban scale modeling is a great asset. And we've also using now more and more geomorphic mapping. This work done by Dougal Townsend and others. They produced a geomorphic map for Wellington City, and the geomorphic expression on the landscape of the geology is often really good for creating subsurface maps as well, especially when you pull in good geological mapping and some of the subfill borehole records as well. You can start to convert those boundaries into geological units. So for Wellington, we created a new interpreted geological map based on all of that information before, as well as a map of all the different fill units as well for us to use in our 3D study. Now, geochronology, it's quite challenging in Wellington, but these geologists from NGO have been using it to understand the sedimentation history at sites, but it's something we need to consider more in our studies because it makes quite a difference. At Te Papa, the museum hotel, the New Zealand museum here, in one report it says that no samples were older than the last glaciation. So in the 3D model, we'd have to have this big dip here, this big channel for our late Pleistocene into our mid-Pleistocene sediment. But if we interpret a contact at maybe 60 meters below the surface where the sediments change, we get back into the much more layered stratigraphy. Which one's correct, I don't know. We'd need to go and resample these boreholes, but the geochronology does play a big role in our understanding of the subsurface. And then some of the best data can actually come from our experts. So expertly derived data, or some people call it manually created, but basically taking all that intuition and history that a geologist has for a region and putting it into the 3D model, particularly in places where we don't have subsurface geological records or good mapping. Is using all of that information and adding it in. So forget about artificial intelligence. Now it's all about geoscience and intelligence, the GI. And there's also other problems, not all the data sets agree. So the likes of Wellington waterfront here, the depth to basement along the Centreport Ferry Terminal area, it's more than 1,500 meters from the nearest borehole. It's been the attention of numerous geophysical studies, but no boreholes, as I said, over the years. And quite a variation in basement depth from 150 meters back in the mid 70s to the current studies are still disagreeing quite a bit on the depth to basement. So until we put the big pointy lie detector in and drill a hole, we really won't know what the true depth to basement is. But then, what is basement? Do we base it on where our geopic bounces back up and hits us? Is it a really hard rock, or are we talking some sort of geophysical basement? We might have a weathering horizon, or is there some sort of pseudo basement down there, like in Upper Hutt, this unit B sitting down quite deep below, sitting on top of the basement, imaged in seismic data here of some buried gravels. So yeah, it could be the Taniwha hiding under our harbour there. But maybe these guys that saw this drill rig out on the harbour the other day, that's a picture from LinkedIn, they're drilling there now by the ferry terminal. We'll see how deep they go, if they can answer some questions for us. So what software do we use? Well, at GNS, I'm really lucky. I've got a lot of tools at my fingertips to play with. Primarily, I'm modeling in Leapfrog. It's one of my preferred software suites. They don't pay me to say that. It's just the one that I have access to the most. But there's all of this other software that you need for manipulating your data, doing a spatial analysis, storing it, that you need to have good control of all the way through with your data. And we're now also moving into a new realm of machine learning and AI for our 3D modeling with code-based 3D. So if you haven't heard about it, check out the Loop 3D work as well, but also access to freely available software like QGIS is also really good for managing our data. So what's the modeling process? Well, basically you just throw everything you've got at it and go for it, and then a final model pops out at the end. This isn't a tutorial on 3D modeling, I'm not going to go into that, but basically you work your way through the data and then voila, a 3D model. So this is the 3D model of Wellington City, taking into account all of those data sets I was talking about before. And, you know, a 3D model is more than just a pretty picture. Obviously, these are pretty pictures. I'm not going to make you all seasick with a fly through today, but, you know, we can interrogate it through sections and different areas. Here's one looking through the Centreport region across Wellington Harbour. You can see we've got quite deep sections of sediment, good vertical exaggeration on that to make it a bit more exciting. Looking north here through the Miramar and Rongotai basins and the oblique view south here through Wellington. So that's our current city 3D model. And then we've got our regional geological model, which has much fewer units. It's really just a basement and a few sediment layers on top of it, because this one takes my computer maybe a weekend to run. I've got a fairly grunty PC here at GNS, but there's a lot of cells and a lot of thinking involved. But you know, the outputs of that are these regional elevation models that you can do that can be used by other people. So what can we use our model for? Well, we've got all sorts of things that can come out of a geological model. One of the first things that I'm usually asked for by people is, what's the depth of the basement? You know, that Z2, that Z 1.0, or we can do forward modeling of site period. So you can go out and measure site period. The geophysicists can do that, but they can't get everywhere. So maybe we can use the geological model if it ties in well with the measured data to forward model site period, or even VS30 as well. We can use it for ground conditions for liquefaction studies. We can backflag on our boreholes to see how well our interpretation was, or how well the model's performing, or evaluate it onto other data sets or surfaces or anything like that. And then we can start to generate other data sets as well. You know, we can create 3D shear wave velocity models. What's our depth to the loose dense surface, maybe for a geotech study. And then I was talking about the very clever numerical modelers that do the ground shaking and ground motion studies. But also, you know, just geotech companies, you know, program planning. At my site, if I need to drill the basement, am I going to have to drill 20 meters, or am I going to have to drill 200? So I might not be able to tell you exactly how deep basement is, but it should give you a pretty good idea, looking at a model like this, how much you need to include in your budget to hit basement for your client. So I'm just going to talk through just a few examples of these outputs. One is depth to basement. This is one of the, as I said, it's the map I'm asked for the most. So you can contour it, you can grid it up, you can do all sorts of things with it. You can compare it to where your borehole data is. I'm just showing the open file ones here, not the closed file ones that sometimes used in research. But you know, in the Wellington CBD, we can see a basin in Wellington with sediment thickening up to the north through to Papa here. And here's our waterfront area that I was talking about before, that we've got our depth of basement problem. You know, this most recent model, it's still interpreting basement as quite a bit shallower than some of the gravity surveys. So it's an interesting problem that we have to solve, and there's some people at Auckland University that are keen to get stuck into that one as well, by looking at all the data and trying to understand the problem a bit more. And recently in Miramar, the gravity line done across the basin, and you know, it showed us some quite interesting results about what was happening in this little block between the faults here. So depth of basement is definitely one very useful output. We've been using it recently to forward model site period. So we can do this in 3D. I'm showing a 2D section here as an example, but basically we can take all the different thicknesses of the units. We can apply some shear wave velocity units to them, and then a very simple formula allows us to calculate the T0 value for each of these sites. And we can also do VS30 quite easily just by juggling around the formula to output just what's happening in the top 30 meters. But yeah, really easy to pull out thickness maps from our 3D models, because that's one thing that obviously that goes into our site period model. And you know, one thing about having lots of geophysical measurement on the surface that have measured site period is it allows us to see if our 3D model is behaving well. So we've got a reasonable understanding of what the shear wave velocity profile is, but if we compare the 3D model calculated site period with the measured site period, we get a pretty good fit. I'm actually pretty happy with this as far as the range of error goes in the site period measurements. We do see some, up to about 1.2 seconds here, the model's doing a pretty good job. As we get into the deeper units, we've got this little subset of data up here. So these red spots, these are the best site period measurements. They've been quality ranked a bit like our boreholes. So for the 3D model to try and pull these in back closer to this line, we need to reduce our depth to basement by 25 meters. So make it shallower, that is, by 25 meters, which goes against what all the other geophysicists are saying is happening, because this is the data up by Centerport. We want to make these deeper, not shallow, or start changing around with our shear wave profile. So yeah, this is some fun and games there for people in the future. But if we've got a reasonably good fit and we're confident about our middle units, we can then start to apply that site period model in areas where we don't have a lot of site period measurements. So this area in Miramar and Rongotai, we can create a site period map, our all important 0.6 second contour. We've only got a few stations here was measured, so we can use our 3D model then and be reasonably confident that we're understanding the site period based on the underlying geology, if we got that right. Fill thickness mapping, obviously we can pull information out from boreholes in a 3D model. You can see Wellington's had a few generations of fill. You can see here between the 1930s and more recently, we've had a lot of fill added on, up to 20 meters out here around the ports, and you can see it increasing in thickness out towards the harbour, so we can understand where our fill is, because that behaves quite differently during earthquakes, and or if we're looking to extend buildings in the city, understanding how thick our fill is. One of the other ones I was talking about was not just working with shear wave velocity in set blocks, but we can start to do 3D evaluations of shear wave velocity. So we can use these best fit curves from the downhole measured data that we have and apply those to the distance from the surface down and create 3D VS models, which it still needs a bit of work, but we're getting there with that. And there's lots of really clever people out there doing some fantastic numerical modelling studies. We've got Chris down and Robin at University of Canterbury doing amplification of ground motions and ground motion simulations. And recently interesting studies starting off here at GNS by Andrea, looking at how the buildings affect the ground motions and each other. So a real good crossover of different disciplines in that study. So if you're interested in those, get in touch with those people. I'm sure they're more than happy to chat to you about some of those. And obviously there's probably lots of other end uses as far as numerical modeling goes. Extracting site information for planning. So if you're a geotech and you've got maybe a site here and you're looking to put in 5 boreholes, what's under those, what conditions do you like to reach, and how much money do you need to budget to hit basement in these different areas? Pull up a rough section of the geology, look at it in the 3D, you can evaluate all sorts of information in the 3D model for end use. And then, as I mentioned, the NZGD, the geotechnical database always has new data coming into it. So each Monday morning, I make myself a cup of coffee, download the latest data from the NZGD and see what's new. And for example, a few weeks ago, these 4 boreholes popped up on the Wellington harbour front. Tonkin and Taylor did this in 2021, and they got them up there recently. I've got some beautiful logs. I've got 2 boreholes, one here and one here, which hit basement. And if you've done any work in 3D modeling in Wellington, you know that any sort of basement intersections are actually gold mine data. I've even got some pictures of the rock and digital data in AGS format. So I can quickly add those into our borehole database, hit rerun on everything, and the 3D model updates and reinterpolates the surface through these 4 new boreholes, where you can see that these blue blobs here. This is where I had data before, and now these boreholes here are helping constrain where that surface is going. So always good to have new data. So our 3D model, it's almost live, and we're always updating it. And then just the final bit of this presentation, I just want to touch on uncertainty and confidence in 3D modeling. Now, mapping the confidence in our 3D models, it's an ongoing challenge, and there's been a lot of research into this in the 3D modeling community at the moment, and there still aren't tools that are easy just to implement in our 3D software to calculate what the uncertainty or confidence is at any point. Some of the academic research that's going into the 3D modeling uncertainty it's often focused on the dip and strike of contacts or the interpolation of data as it runs through. So it doesn't really apply that well to our urban 3D modeling where our contacts are all below the surface. We don't have structural measurements or other surface contacts the same. But when we think about our 3D model in Wellington, it's our confidence really is how close are we to data? How close are we to the nearest borehole? Are we way offshore where no one's ever drilled before? Are we well away from where good mapping is because it's all under a huge amount of scree? We don't have good surface mapping. So we can derive our uncertainty and confidence using basically a distance from where we've observed data. And back in 2019, I had a first crack at it. I sort of came up with 4 different properties, distance from surface and basements and boreholes and the quality of borehole, classified each one into 5 and gave myself a rank out of 20 and just added them together. I've got 10 fingers and 10 toes, so the math was reasonably easy on that one. And, you know, it gave us a reasonable idea of where we were most confident about the area in Wellington. But recently I thought I can do a bit better than that. So I've been looking at 3D fuzzy logic. So fuzzy logic, it's a technique that's commonly used in 2D spatial analysis to combine maps of different data sets. And basically we assign a membership value to each data set that we want to consider, or a distance from data sets, based on how confident we are at that distance from the data. So we either say, oh yeah, we're okay here, or we're too far away, we're not confident when we're back at sort of 0.1 or 0, or if we're right near a fantastic borehole and good mapping or something, we can give it a high value. Then we put all those into our into some fairly simple math and come up with what I'm calling at the moment is fuzzy confidence in 3D. So these are just some graphs. We're still tweaking these to sort of work on the exact values, but you can see that, you know, as we move further away in our distance, our membership value drops from 1 down to 0.1. You know, as we get further away from our, you know, this is a really good quality number 5 borehole, and as we're sort of getting 500 meters away from it, sorry, that just say meters, not kilometers, 500 meters away from it, it is decreasing in our confidence in the area away from it. And we do the same for distance from ground surface. And ruggedness is something I've been integrating because, you know, if we're just dealing with borehole data, we don't have a lot of structural data. You know, where we're dealing with steeper slopes, if we're penetrating that with just one borehole, you know, we don't often have a good idea what's happening in 3D on those steeper planes, or where the surface is more diverse in slope. So obviously where it's less rugged and flatter, we've got more confidence that our boreholes are telling us what the orientation of the plane is. And as we move away from that, as we're getting into steeper slopes, our model is less accurate. Yeah, so, and, you know, proximity to faults, you know, obviously when you're getting close to active faults, some really interesting things happen near active faults, especially when they start to go around bends and things, they get very complicated. So we can incorporate that in, and all the time using 3D distance functions and interpolations of data to help understand things in 3D. So when you go through and you calculate that in your 3D model space, you get this lovely visualization of fuzzy confidence. We can plot it out as a block model. So this here is looking south. Here's the Wellington CBD area here. So we've got quite good confidence. We've got a lot of boreholes in through here. We've got less confidence as we move out into the harbour, or as we move away from the surface or along our fault zone. So those are some of the data sets coming in. So we can visualize that confidence maybe on a plane. This is the top of the basement, or the top of the Rakaia Greywacke. So you can see our depth to basement understanding, you know, is pretty poor as we move out away from our boreholes and into the harbour. But up around where we've got borehole intersections or good mapping, and, you know, the different quality of mapping, whether it's well defined in the geomorphology and sticking out of the ground, or if it's undercover, is giving us a different confidence for understanding our depth to basement down there. And then, you know, we can interpolate that onto sections to understand what's happening, you know, along a particular line, or onto our boreholes for maybe planning, you know, if we want to know something. So there's all sorts of uses for understanding our confidence in the 3D model. Right, well, just to sum things up now, basically over the next few months, I'm in the process of writing up a report on the region and city scale models that will be publicly available from GNS. This is through the National Seismic Hazard modeling project. And all the 3D models and surfaces will be available as digital appendices for people to use. It's the first time I've been able to get all this data out in the public arena for everyone to use. So that's our goal. We're always incorporating new data into our models. Particularly the borehole records, so from the NZGD and from all the great companies that are working around Wellington that send me some of their research, send me some of their data for research purposes if they can't be made public. So thanks for that. So yeah, our 3D model is effectively live. So if a lot of time has passed and you're watching this recording in 2 years' time, just get in touch with me to see what might have changed and for current versions of the model and what's happening at your site. Or if you have a research project that can use the 3D geological models here, please get in touch. Or if you've got, as I said, data to share, yeah, get in touch with me or others in the research team. So yeah, thank you very much, everyone, for listening today. I'd just like to thank all of these people. This work in Wellington is by no means a one-person show. There are a huge number of collaborators and both research groups at all the different, lots of different universities, the GNS and university scientists that we've been collaborating with here at GNS, and also our friends in the industry who send me data and evaluations. And yeah, thank you very much for that. So, yeah, that's me. Thanks, folks.
Oh, thanks, Matt. I think that was a really, really good presentation from basically going from right at the very start and having the boreholes and the raw data there through to outputs and what we can do with it afterwards. I know, especially with uncertainty, that's sort of, I think, a lot of something that we all grapple with quite a bit. So I guess to all the participants, keep the questions coming through and we'll go through them. I'll kind of just start at the top. Matt Reeves' question, I think you kind of answered at the end, but I'm going to put a slight sort of twist on it. His question was, will the 3D models generated by GNS be available for the general public? Which you said they will be, which is fantastic, I think, for everyone, for all of us. The twist I'm putting on it is, I guess, will, as they are updated, will they be sort of regularly updated online or for the public to use?
That's really tricky at the moment. We'd love to have a live version that people just interact with online. We'll see where the software takes us in the future. Basically, because there's not a lot of end users for the 3D models, I'm just encouraging people to get in touch with me, as I have over the last sort of 5 or 6 years doing these things. Is, you know, just if you've got a site in Wellington and you're interested in it, drop me an email and I can chat to you about the 3D model and the data that might be underlying it and things like that. And it is a bit tricky putting 3D models online because someone could take it, yeah, do all sorts of things with it. But yeah, we'll see how the future goes with interacting with 3D models in a live online environment. Yeah,
that's fair call, definitely. And I guess the next question was, is there a way to contribute new observations that don't fit into the NZGD, which is, I guess, what you mentioned of email you, and is probably the easiest way
anything you've got. Yep, I'm a data hound. Yep, and you get your name in bright lights at the next talk. And yep, no, if you've got any data you'd like to contribute, or if you're drilling a hole and it's, you know, or if you're about to drill a hole and you want to try and win the office pool on depth of basement, I could be your secret ally with the depth of basement pick. So yeah, get in touch.
Cool. You can tell there's a few questions along the similar veins. Lee was wanting to know if you'd like to see any changes introduced so that companies, when they're drilling or commissioning boreholes, share their data in addition to the sort of voluntary NZGD.
Yeah. So most of the companies in Wellington are really good. They get their data up in quite a timely fashion. There may be a few that don't. Yes, I would like it to be compulsory. It is in some cities. I think Auckland and Christchurch, as part of your consenting phase, is uploading it into the NZGD. If anyone is wanting to talk to the councils about it, touch base with the guys at the NZGD because they have done this before. They've been through it, and yeah, just get in touch with them, and they can work with your councils to streamline it based on what they've done in other areas. So, yeah. Yeah, I would like to see it compulsory, but I understand that there are some more sensitive sites. But yeah, thanks for the question.
Yeah. Is there, Simon is wondering, is there a possibility that you could do all of New Zealand in a 3D model in the near future. I would imagine it would take some sort of supercomputer to do it.
Well, change the scale of the data, not really. It has been tackled here at GNS. Please get in touch with Mark Gradenbury or Katie Jones. I'm trying to remember who the 3D modeler was in our Wairaki office that was working on that. We have had a crack at it here at GNS. I haven't actually seen it, but yeah, it is possible. But you know, to compute it, like you were saying, Christoph, is at any, depending on the scale, it's going to take some time.
Yeah, definitely. Cameron was wondering, I think this was in relation to some of the work that you've been doing with the geomorphological mapping and the historic aerials. Have you used any particular techniques for getting more geology out of the LiDAR data, or was it manually working through the DMs?
Right, so the LiDAR is just the gift that keeps on giving. It's fantastic data, especially in built-up urban areas. There's some of the new LiDAR that was just released for the Wellington city area. I think it was last year it came out, has been filtered really nicely. So we've got a good digital terrain model, a DTM. Really, you just sort of throw lots of different GIS filters at it. I quite like some of the sky view techniques. But often for geology and geomorphology, it's your hillshades from multiple directions that really plays a part. But there's you just go on YouTube and look up LiDAR interpretation and start looking at some of the different tools. The tools that work the best different from area to area. So maybe what I'd use down in Murchison in the South Island, I'd use completely different analyses to highlight different things in Wellington and different techniques and different scales of the point density and things like that. So what I usually do when I start a new area is I throw all my bag of tricks at it and see which is starting to tell me the best evidence or pull out the best features. And that's, yeah, start with a hillshade, then throw your bag of tricks and what works, and then go from there.
Cool. Joe was wondering, what is your biggest lesson learned in the data collection modeling process? It's probably a very good question to ask, seeing a lot of us do it.
Yes, we do have more confidence. There's the work by Anna Kaiser, myself and others in 2019, I think it was, that started to revise that boundary. And that was using a lot of site period measured geophysical data, and then the 3D model filling in space around that. And obviously, as the model is refined, as new boreholes come online and we regenerate surfaces, as the great researchers do more geophysics and gravity work and things like that around, you know, we're always pulling that into the model. So all the time that CD boundary is being improved. But I guess the CD boundary is, it might be an old data set now. It's just starting to move into VS30. Yeah, so yeah, but definitely we are gaining confidence all the time with all that new data going in.
Yeah, CD is definitely interesting. And overall, what do you think? I think this is probably a nice question given the time to round it out. Your overall biggest lesson that you've learned in all of this process?
Probably that the 3D modeling side of it takes about 1/4 of the entire time of the project. So yeah, there's a huge amount of data prep and spatial analysis and cleaning of the data that needs to happen beforehand. So if you're a geotechnical company looking to undertake a geological model of any size, make sure you factor in a huge amount of data cleaning, but also make a lot of friends who may have already cleaned the data historically. And yeah, and then understanding the purpose right from the get-go of what the model is going to be used for.
Yep,
will probably be it.
Cool.
Yeah,
I think that sees us out pretty nicely, exactly on 1 o'clock. So yeah, big thank you again, Matt, for giving this presentation. I know a whole bunch of us will really appreciate your insights and knowledge to the work you've done, and I think all of us look forward to seeing those models and reports come out over the next few months. So yeah, appreciate your time, and yeah, if anyone has any questions, feel free to email Matt, I suppose, and email him your data. It'll help us all. Cool. Awesome. Thank you very much.
Thank you.